All right, this is the lecture part of Class 18. I'm sorry for the noise in the background. The 3D printer is making whining noises, as many of us do when we're home alone for this long. All right, so preloaded bolted joints. This is your basic preloaded bolted joint. Here, this is like a pipe with a flanged end with a blank. So this would be just sort of the end where there would be nothing connected onto the end of the thing. And what we do is we take a wrench and we tighten down the nuts on these bolts. And when we're doing that, we're making the bolt, we're increasing the tension in the bolt, but we're also squishing, right, the member. Right, so if you can imagine that the thing was made maybe out of some spongy material, that it would actually deform, and it does deform, but it's very hard to see it. It's a very small amount of deformation, but it does deflect, and the bolt does stretch. So this part of the bolt gets longer, and these guys get smushed together, and so there's a nice large compressive seal in between these two surfaces. And this is an example of a use of a preloaded joint, and it's on the head. These are considered the head of these large slow-speed engines. So that's this portion right here. You could see it up here, and here's my friend Brian. Right there, labeled. That's Brian. There's the head, and you remove the head, and then you can remove, and this, by the way, that's the piston and the and part of the connecting rod. The connecting rod actually has this long straight part and then a swiveling part right here. It's called a crosshead type of arrangement, and you could just get a view of how big these are. Well, the bolts are actually really, really long. They're actually these long threaded rods. You can see them right here. I pre-circled this thing, and you can see how big this dude is, so you can actually see how long they are. And what they do to tighten these down, instead of trying to use a torque wrench, they actually have this hydraulic cylinder. So this is the part of the bolt right here. It extends downwards, and this is the threaded region. And what they do is they put this big mount right here, this hydraulic portion in here, and they screw it onto the screw, and right below it, this is the actual nut that's on here. But what they're able to do is they put in a hydraulic pressure right into here, and they lift this thing up, and they actually stretch that bolt enough so that they can actually measure the amount of deflection. And so they use this dial indicator, and they put the hydraulic pressure on there, and when it's deformed enough, they know how much strain is inside this bolt, and therefore they know how much stress. And since they know the stress, they know the force, and they know the preload force of this bolt it will be holding down. And then once they have that level, then they just take a little rod right here, and they just tighten down this nut. They don't have to tighten it down very much. When they release the pressure, this tension stays inside the bolt. It's an interesting application of a preloaded joint. And the idea is, this is the part of the head that you're not seeing right there. The head gets pressed up against the cylinder, and here's like maybe an example of an FEA showing the stress distribution around the interface between two flanges. So this would be a plot looking downwards of this region right here, of course, but you're looking at it from the top. And you could see that what we want to do is be able to have enough deformation here so that it's going to get worse and worse around the bolt, right? The deformation, enough so that the pressure between the bolts is sufficient enough that things can't leak by, right? So that's our goal. And in order to do it, we want to have a competition between stiffnesses between the bolt and the thing getting bolted. So when we go to do that, we want to create the bolt stiffness and model the bolt stiffness. So we can think of the bolt as having two essential springy parts. The shaft right here and the threaded part that's inside the joint. The only thing that matters is the stuff that's going to get stretched, right? So it's from the nut to the head of the bolt. And you could think of them as being two springs, or say, let's say, springs in series. And if you think about what it would be like to hold a spring in two springs and connect them in series, and see that they would become much stretchier than the two, than if they were in parallel, right? So, like, if we were to open this up here and let's keep what we've written right here, but let's see. I want to get my camera started. So how do I do that? I go up to here and write camera. Okay, it's gonna give me my camera. And you're going to see upwards right here. So right there. Okay. So if I have these two springs right here, and one of them is stretchy, and these are equal to each other, if I go and I connect them, if I can, I haven't connected them here. All right. All right. I think they're connected now. See, now we've connected them in series. It's a lot easier. It takes less force for the same amount of deflection. But you could imagine, though, if I put them in parallel with each other, like this is twice as hard, right? So they add together when they're in parallel, but when they're in series, they add together very much like, or similar to, analogous to a. What happened to this stuff? Oh, okay, I see. Very analogous to the opposite, maybe, of resistors. Now, I believe maybe it's capacitors that actually add this way right here. So, when we want to get the total stiffness, we take 1 over the total is going to be equal to 1 over the individual ones, right? And so this case right here. And by the way, if these K1 and K2 are equal to each other, the K total is just going to be 1/2 of the K of either of the Ks, right? Because they're equal to each other. So that's the stiffness. But these are bolts, and you got to ask yourself, well, what is the stiffness of a bolt? Well, this is not a difficult derivation to make. You can take the stress is equal to F over A. You could take the strain is equal to del over L, and you could take the stress and relate it to the strain by Hooke's law, right? So plugging those into Hooke's law, you'll find that F over A is equal to del over L times E. And we happen to know that stiffness, by definition, is F over del, right? Force over deflection. So we're left with AE over L. So now with these, that's the individual stiffness. So now we need the area and the length and elastic modulus of that part, and the area and length and elastic modulus of this part. So what we want to do here is we would find that K, and we'll call the threaded part T. We'll take the area of the threaded part, and we find that in a table, times E, and divide it by the length of the threaded part, which is this guy right here, between here and here. And then we find the stiffness of the bolt of the shank part. Let me see, I'm sorry, not the B, but the D, right? They decided to call that the KD is going to be the area of the D times E, and of course it's the same material, and the length of the shank part, that little LD. So we find that KB, when we do out our math up here, if there's only two parts to it, it just ends up KT, KD over KT plus KD. We substitute and rearrange, and we get AD times ATE over AD LT plus AT LD. And so this is equation 817. And in getting this bolt, in getting all these values right here, so one of our obstacles to doing that is to finding all of these dimensions. And you need to go and look carefully at, let's see, we'll keep all this, delete it later. You need to go to the book. All right, so first off, make sure we're on the lookout for this guy right up here, right? This AT right up there. So we can find it for like, say, for half an inch bolt. Where'd you go? Right here. Right here is 0.1419 is the area, square inches for the, what we're calling the tensile area. And they actually give you sort of a means of estimating that and calculating it. But in order to find those lengths, right, we have to go to this table and analyze it very carefully, right? So there's lots of things going on right here. And we have two scenarios. We have, well, the one on the left is going to be when we have two things in between, two pieces of material in between, and the nut is on the outside. And then the one on the right is when we have a threaded piece where we thread into the piece. We need to go through and march through this thing step by step to be able to get this. Now, do I have this later on in the book, in the notes? I mean, no, I don't. So this is the place to do it. So when you're trying to get these lengths to be able, our main goal is to get little lt and little ld right here out of this. Well, you start with that you have, I like to call it A plus B, because that's the, a lot of times they'll make the dimension of this one in the darker gray A, and the one over here, this thickness of the lighter gray is B. And that's going to be the, let's see, did we ever write that anywhere? Thickness of all the materials. Okay, so we're also including in if it has, say, a washer right in there. Most of the problems we do, we're not going to put the washer in there. But we find that little lowercase l, and let's see what we're saying here. So, no, that's for figure B. So don't worry about him. We're only looking at him, right? So that's little l. And then we say we want to find the fastener length. What we do is we take L, a big L is going to be that little l plus this big H. And you might go, well, where does this big H come from? It comes from the nut thickness. So that we get this from table A31, which is in the back. Right, so we look up the nut that we want to use, and we're able to find H. So what we find now is we found that big L, this big L needs to be bigger than little L plus big H, but then rounded up to the preferred sizes. But you also need to have, I think this asterisk might tell you that you need to have at least 2 threads. So yeah, okay, so they might not be available in all things, but there's an important thing to note, that you want to have at least 2 threads. This guy right up here, you want at least 2 threads hanging outside the other side of the nut. It could make it difficult to put the thing together otherwise. Anyway, so we want to get the threaded part, big LT. That's going to be this right here. Now this is just taking, I believe it's sort of a rule of thumb, maybe it is an industry standard, 2 times the diameter plus 1/4 inch, and that's going to be what the threaded part is of a regular bolt. Of course, you've probably seen bolts that are threaded all the way up, so that's not 100% true, right? But that's what we use here. And then we figure out what the LD is going to be, the little LD, the shank, right? This is the unthreaded part right here, is going to be the part that's the length of the whole thing minus the length of the threads, and then the length of the threaded part inside the grip is going to be the entire length of the two parts, right? This little L minus the length of the non-threaded part. And that's how we get to those. I go through that because I find that many students, they don't read that carefully. So I figured maybe I would put that into this section right here and just spell it out for you. Now, in order to model the stiffness of the member, we use a frustum, which is really just a cone, right? We take a cone, two cones really, and we lop off the tops of them, right? And then, of course, they're hollow right in here where where the bolt hole goes through. A lot of times we'll assume that the hole is the same size as the bolt in our model, but this actually turns out not to be true, right? You would need to make some clearance in between. So that's what we do. Is we usually come from the head of the bolt, like right here, the outside dimension, and come outwards, and we come down to the slope, and then we do the same thing from the nut and come upwards, right? And then they're going to intersect someplace. Most of the time, if this is the same dimension as this, and the thickness is, it's going to be halfway in between, right? So it's going to be halfway of the distance between the grip right in here. And so what we're left with now is we actually have three of these frustums, right? There's 1, 2, and 3, and I think I have them drawn up. This one of these, this like absolutely upside down. But in any case, 1, 2, and 3. So if you want to get the total bolts member stiffness, it's like 1 over K1 plus 1 over K2 plus 1 over K3. And now our obstacle is to find what is the stiffness of each of these frustums. That's the way. Well, what we do is take, these are really a model, right? These are just supposed to represent springs, and they're trying to say this is the active amount of the spongy part of the member. And over here, I think it kind of gives I like these little lines right there that kind of shows you sort of a stress distribution, if you will, that it's expanding outwards away from the heads. So that's why they're saying, and you can almost think of the strain energy as being contained within this material that we're looking at here. It's really just a model. They could just have easily have made this, in my opinion, a cylinder. Right, it could have been, and that's a lot easier thing to. That's still just going to be AE over L onto the thing, except now you would subtract out the center cylinder part of these two pieces, and now easy peasy just to get what the stiffness is. But instead, they decided to use these tapered thingies, and in order to find what they are, you get K is going to be pi E D times the tangent of alpha. Now alpha is going to be the angle, right? So it's going to be the angle that's like formed right in here, I believe. Let me double check that. Yeah, this is going to be alpha. And a lot of times they say it's 30 degrees, right? So they don't really give you any other guidance, but maybe empirically you would come up with some number, but they always use 30 degrees. So I will show you the equation in Shigley where this comes into play. So we get the natural log, this is the ugliness here, 2 times T. T is the thickness, I believe, of these things. And then that's going to be times the tangent of alpha plus big D. And big D, you wouldn't expect this, is the smaller of these for the cone, right? So it actually turns out this is the big D for this one, this is the big D for this one, and then little d is going to be the hole right here, all right? So you want to be on the lookout for that little d in there. This goes minus d right here. Parentheses, and this big D plus little d, right? And this whole thing inside the natural log divided by 2t times the tangent of alpha plus big D, and then plus little d. All right, so that's the thing that'll catch you, is getting these signs the wrong way. Times big D minus little d. Right? Okay, and so this is like equation 818, and you got to do this for each of these pieces, like 1, 2, and 3, and you got to be careful that you're always using the smaller of the diameters of the chopped off cone for it. So let's take a look inside of Shigley for this. And let's see, we'll zoom down to pages. Is it upwards or is it downwards? It's downwards. Right there. Here's where we have this discussion, and here's where they're giving you the nomenclature. Here's your alpha, here's your big D, here's your T, here's your little d. You get the idea, right? And that they're coming up from right up here, the D, little d width of this thing. And I think the equation I decided to give you was 818. Did I lie about that? I think I lied about it. I guess it's actually equation 819. But they say often alpha is 30 degrees, so you might as well just go ahead and plug in for the tangent of 30 degrees, and now you have this number right in here, right? And some of these numbers fall out. And then they also start to go and say sometimes the grip is 1/2 of the thing, so that shortens the problem down a little bit. And then sometimes they're made of if they're made of the same material, I believe. Yeah, I think it would be here. Yeah, if the members of the joint have the same Young's modulus and are symmetrical back to back, they act as two identical springs, so that you're able to do this in one step, right? So up above this right here is the individual frustum, but down here they've like reduced again the amount of effort. And then sometimes there's actually for a particular type of bolt, the width of the bolt and the nut are 1.25 times the diameter, so you can reduce that even further. Okay, just to let you know that you have a lot of choices to go through. I would say either use equations 819 or equations 820. Maybe 820 is the way to go. Makes it just a little more straightforward in case things aren't symmetrical, but just understand that they're there. And there is some discussion, additional discussion about different relationships that have been found, and from different people who had opinions about how this stiffness is actually arrived at. So these are just models, not necessarily something that you could write home about and say this is for sure. But the whole point of these is to try to see how they interact, the stiffness of the bolt and the stiffness of the member. So the big idea is that when you preload the bolt, you're tightening the bolt and you're stretching it, and you are compressing the member. When you put an external load, and we'll just call it P, is the external load, applied to the outside, the bolts will stretch some more. But here's the important thing: the member will uncompress some, right? It was compressed, but the outside load now makes it uncompressible. And so because these are springs in parallel with each other, they have a certain behavior, so that we can come up with a coefficient that is not really a coefficient, but a fraction, which is the fraction of the external load that gets placed onto the bolt, and that's going to be KB divided by KM plus KB. And this is an important thing to look at, and this is often approximately 0.2 or in that range. There's some examples in the book where you'll be able to see what various materials will often be. But you really should calculate both the KB and the KM yourself to be able to get these values. And then, now what happens, what you use this for, is if you want to find out the force that is on a bolt, you take the force that the bolt has to carry, right? The portion of the external one, they say, right there is this K, this PB, right? Where PB is going to be equal to C times the external load. And by the way, that's external load per bolt, right? So we might have a bunch of bolts, but we divide them by the number of bolts, and they end up getting, like right here, right? We could write that P total divided by N is equal to the P external tensile load per bolt. Now we multiply that by C, and that's the amount, that's the percentage right here. That's what this really is, this fraction. You can think of it as the percentage of the external load that the bolt has to carry. So that ends up being CP, but then it also has a preload, so you have to add that back in, where the preload is FI. And now for the member, instead, the load on the member is going to be 1 minus C, because it's like if this was 20%, now this is going to take up 80% of the thing, and it's going to relieve the compression preload, right? So it is loaded, we could think of it as if the bolt is loaded with FI and tension, then the member is loaded in FI and compression. So therefore you have minus placed onto the thing. Now this website right here, Bolt Science, is a pretty good one to go to and to check out. Let's see. Will it allow me to highlight things? No, it won't let me go. I guess this is actually, this is probably a PDF that I grabbed. So this is not actually a link I can grab to, but go to Bolt Science and check this out. But this is a graphical description of the interaction between the bolt stiffness, which is less stiff, generally speaking, than the member stiffness, which is in green right here. So you can see that the bolt stiffness is a slope, right? So it's a slope between force, or any stiffness is right here, right? It's really the rise over the run. So it's the slope of the thing, because we know that F is equal to K del. So this extension is del right here. So what we deal with is we're superimposing them. One of them is positive and one of them is negative, if you could think of it in those terms. Like we could think, I like to think of it as that, like this slope that I'm putting in green was this one over here, and we just slid it over to so that we could see how they interact with each other. And they touch when there's no loading, no external loading right here. They touch at FI, right? Because they're both experiencing the same FI, the same preload. And so what we have here along the bottom is this is the stretch of the bolt, the deformation of the bolt with preload. And this you could think of as the, right here, in this gap, is the deformation of the member due to preload. And like I said, the bolt isn't as stiff as the member, so the bolt stretches a lot more with the same load on it. An external load in blue gets placed onto the piece, right? So the magnitude of this external load is right here. And now you can see that the whole thing stretches more, right? So like right in here, this is the deformation due to that external load, where the bolt will get longer, but the compressed member will get less compressed, right? So that's the point at which right here that we're dealing with. And interestingly enough, here is the PB, if you will, and right here is the PM that we just calculated on the previous thing right here, or the FM, I'm sorry, it should be FM. So this is the F of the bolt, and this is the FM, right, the force in the member, because it's the amount that's being taken up. Remember, so like, let me take that back. Right here should be the F of the bolt. That's the amount of force in the bolt, the total force in the bolt. And then like right here is going to be the force in the member, if we're going to. So the other thing that when I wrote them as P's, that was the correct one. So that's an interesting way to look at it. Oh, one last thing we should know from this diagram, good information, is that at this location right there, right, as soon as the, like if it extends to right here, right, if we get to this location, this is where the thing will open up. That's where the joint will open. When all of the compression of the member is gone. Now, if you want to figure out how much torque that you want to apply with a torque wrench, you can use the same approaches that we had in power screws. In power screws, we took the threads and took the friction within the threads. We also took the friction in a collar. Here we're going to have a friction underneath the bolt head and underneath the nut maybe. And so it's going to have a resistance to being torqued, and that's going to come up with some coefficient that we're going to put, and we could put that inside right here. So here's the preload, that Fi that I want to find, the necessary preload. Well, here's going to be the necessary torque to accomplish that preload based on the dimensions and the friction coefficient of friction of the threads. And then there's the diameter of the bolt too. It turns out that this K is typically like 0.2. So instead of going through this process, we'll just go ahead and use 0.2 because there's a tremendous amount of uncertainty on what the coefficient of friction is. But we can, through time, empirically find a value that's going to be decent. Now, you remember I mentioned that we went through this process right here of preloading these bolts because they were so critical that they want to have a high degree of precision, so they were able to do that. So it turns out that using a torque wrench isn't a very reliable, not 100% reliable, or I guess it's sufficient because it gets used all the time. But you have to appreciate that it isn't that you're relying on this coefficient of friction in order to get an accurate preload. Another way to do this, by the way, I mentioned this in class, is they do make, well, there's actually a variety of ways of doing this, but they make these washers that can kind of have a taper down to them onto the surface, right? And when they tighten the thing up, of course, this has a deformation, a known amount of deflection that this thing has to have, and they have a stiffness. So when these come down and get flat and has that amount of deformation, you can know what the amount of force is going to be. Kind of a similar, but not quite what this is used for, is also lock washers. They also act as springs. And what they do is they kind of always make sure that there is some amount of tension in the bolt. And also, they also kind of act as sort of a springiness, so that like if the for vibration will have a less of a chance of loosening up that bolt. Vibration can loosen up things though. We want to know about the strength of the bolt. That's often what one of the main things that we're interested in. And bolts usually go by proof strength instead of going actually through the material strength. They take the bolt as a whole and evaluate it and say this bolt is this strong. Or you can think of the word as proof as being like something that the manufacturer has to prove to the specification body, that they need to prove a bolt is capable of doing this strength, right? So that's and you notice that it's below the yield. Usually we kind of use that proof as being this is the limit that the bolt can handle, and we don't pretend that there is a margin there, but there might be some margin. Notably, some of those margins might be taken up from stress concentration or various other things that they want to allow for. It's the manufacturers sort of covering themselves and saying, hey, we're good up to this point. One aspect that I thought was very interesting, is the difference between rolled threads and cut threads. Where cut threads, you would use a die, right? Or you would put it on a lathe and you would cut the threads. Rolled threads are, a machining a process where they heat up the material, and then they, just as it sounds, they roll it through a machine that puts those threads in, makes those indentations in there, and the process there reforms the grain boundaries, so there's very advantageous to the grain compared to the grain boundaries within a severe case here, where you can almost see here when they're cut away, the grain boundaries remain what they were to the raw material. So that this is a good slip plane for them to go in. And when they're rating these, when you want to find the grade, these are usually the grades. SAE, the Society of Automotive Engineers, their grades will be represented by these symbols on the top of a bolt, right? So let's see, do I have my camera out still? You wouldn't you know it? It's not on there. But we got recent ones, quick searches, today in history. We went for the camera. No, not today in history. That's not what I want. All apps. Oh, here you go. Apps. All. You're gonna make me do it, aren't you? All right, you bastard. C. Should have left it on. All right. So right here. And there you go. And usually this is like a manufacturer on there too, right? So I don't know who FX is. By the way, we could have other bolts. Like here's a metric one, right? So metric is actually listed a little differently. Trying to see if I can get this up. Let's see, what does it say? This says. It doesn't say anything. It has JZ 10.9. A JZ 10.9. I don't know. So JZ is probably the manufacturer, and 10.9 is probably the metric specification. Is this guy any different? He is an R. Right, so it's a smaller bolt with an 8.8. And you can't really see that because of the reflection that's in there. But that's an R and an 8.8. And what that does for us in our strength section of the book, right here. Okay, so here you can see, here's some of the symbols that they're talking about and their types, and they're talking about the proof loads, but you could see there's the specifications right there. They're telling you some things. And here is like the symbols that we're thinking. So we can assume that's a grade 5 because of the bolt that we just saw, the US units. But we could go to the SI units, and you see you have a 10.9 right here and an 8.8, right? So now you have what the proof strength is going to be. You can also find the endurance strength. They don't have as many of those listed. This is later in the chapter. Here they're talking about those proof loads right there. And here's some endurance strength. So they don't have them listed for all of these, right? But they do have grade 5, grade 7, and grade 8 in SAE. And you can see and these are fully corrected. I'll point that out, fully corrected. And then also repeatedly applied axial loading, fully corrected, including a stress concentration as a strength reducer. So that's where that gets placed into it. And so if you want to do an evaluation of a bolt, you need to come up with a safety factor. And that safety factor is usually based on the stress versus strength. Right here, and it is in there, but there's a couple different varieties. So the bolt stress, just remember, is FB over AT, right? And that AT is that's a theoretical stress, really. And remember that bolt stress, bolt force is CP plus FI over AT, right? So that's just the basic of stress. So if we want to get a yielding, they call it yielding safety factor. I think it should be the proof, because they're using the proof strength, which you would find NP is SP divided by CP plus FI over AT, just as we have up above. Therefore, we have the equation that looks like SP AT divided by CP plus FI. And this is equation 828. We'll check those in a second. Now, sometimes used could be the load factor, which isn't the same thing as really a safety factor. It's more of a measure of performance. And what this idea here is it's the remainder of proof load. And we could establish that a proof load is maybe proof strength times AT is maybe the FP, maybe the proof. I don't know. That's maybe not the right way to write it. And then we had like and then so we go the portion of external load carried by the bolt. All right, so we can think of that we've already removed some of the strength of the bolt or some of the capacity of the bolt by putting a preload on it. So this is how much, right? So we've taken the proof load and we've subtracted out the preload. So that's how much we would think that the capacity that it has. And then we would take it and divide it by CP. That's the amount that of the external load that the bolt is taking up. So that is you could think of it as a safety factor, but it's almost more a measure of how the bolt is being used, because it really takes out the preload out of the whole thing. We have a joint separation. That's going to be when you have now you got to think about the preload of the bolt, preload of the member, which is the same thing as the preload of the bolt, divided by, just like above, the portion of external load on the member, right? So or how much the member takes up. And that means when this equals 1, right? And remember that's 1 minus C right here. When this equals to 1, I don't have the equation number written down. When that equals to 1, that means that the joint is going to open up. That's the same idea as this right here, right? That when this preload right here, when this portion, right, this is the portion that's taken up, equals this preload right here, that thing opens up. The joint will separate. That doesn't mean it will leak. It'll leak a lot sooner than that, because that means that it's not in contact anymore. If you remember to come back up to here, it needs to have a sufficient enough pressure in between the bolts to avoid leaking. And so that's a much higher standard to maintain than just the joint separation. So that's not necessarily when it's going to leak. And then when we get down to here, the recommended preload that we might want to experience, they say it should be, as a rule of thumb, 75% of the proof, right? So that's actually going to be 75% of SP times AT, right? That's the proof load. This is when it's like reused bolts. Here they say 0.9 FP or 0.9 proof strength times AT. I call them one-time use. They call them permanent joints, right? Well, I don't think that's right, because these are all non-permanent joints. That's the title of the chapter. We get into fatigue. Now, fatigue methods mentioned in Chapter 6 are directly applicable. Something we should note is statistically, bolts tend to fail 15% some of the time underneath the head of the bolt, 20% at the end of the thread, and 65% of the time at the nut and face interface, the nut right here. So taking a look at that right here in a bolt right here, right? So that means that they said 15% of the time is going to be right in here. Where's my numbers right here? I didn't write it down. Yeah, 20% of the time right here, and then 65% of the time and right in there. So you can understand that's that kind of makes sense, that would be the spot where that would fail. And there's a number of equations when dealing with this. Okay, we already looked at this endurance strength, and I already mentioned that the Kf right there, the stress concentration, was already built into this fully corrected endurance strength. If we want to get the alternating stress in a general scenario here, we take C times P max, external P max per bolt, minus P min, and divided by 2 times AT. And then if you have the mid-range stress, is going to be C times P max plus P min, just as you would guess, but plus the preload stress, right? So this is equation 835, and this is equation 836. And now if you want a safety factor, you want a generalized safety factor between this alternating and this mid-range using Goodman, we would find that the fatigue safety factor is going to be SE times the ultimate strength, so you would need that still from the earlier table, minus the preload right here. They just did the algebra for you in Goodman. That's all this is. SUT, the ultimate strength times the alternating stress, plus the endurance strength times the difference between the mid-range and the preload. And I think that's a generalized formula that's going to be 838. But beware. There are many formulas in this section of the book, and this is a pitfall, and it does reveal a lack of understanding on your part right here. So here are the equations that I just alluded to here for the mid-range and the alternating and the mid-range. And they go, and then here is the equation that I just mentioned right here that you should use. I believe I call this 838. I'm not sure if that's I think they just did a little bit more work right here. Yeah, here's 838. But now they start getting into the discussion of special cases right here. Oh, look right here. Here's a special case. That is when the force is a minimum. Right, when the force that's the minimum is 0, we have this special case, and then they start coming through, and they also are accounting for, in that case right here, that the mid-range is equal to the alternating plus the preload stress. They apply Goodman right here, and now they have this equation. If you use this equation, and you shouldn't use this equation because it came from these assumptions that were right up here, you are not applying engineering knowledge. You are plugging and chugging. And that is a no-no. Do not do it. And you might even be more tempted down here. Here's another version of the thing, but I think it's still what you need to do is that 839... Let's see, I think, am I right up there? Yes, right here, they're still in that condition. You have to read carefully when you look at an equation. Here's another opportunity to mess up. What this is doing is giving a discussion and trying to tell you what happens when there is the benefits of preload. right? So here is the safety factor if there were no preload, so that you could see that sometimes is actually a fatigue benefit of having a preload. That's that's what the point of that section is. But more importantly, do not use the wrong equation. All right, so I think I'll do the example as a separate thing, because this has been a really long, oh, I'm afraid to look at the length. 49 minutes. God help me. But I've recorded a couple other times before. This is interesting to see what the other length of them want. But I'll make the example as a separate thing. Although I already did it in class. So I think I'm being a really nice guy by making these all over again. When truthfully, it might be like the third or fourth time I've actually recorded this particular lecture. But it's an interesting topic, and I don't know, what kind of guitar should we show for as a reward for listening to this really long thing and listening to that stupid printer, and then looking at my mask right here. So it looks pretty good, doesn't it? This guy hadn't come up yet. Nice. That's not in tune. I don't like that tune. I'll use this tune. So this is my Godin nylon, classical style, but it actually has a MIDI pickup in it. So it's got this 13-pin connector in there. You could trigger a bunch of MIDI sounds. Well, if you use the MIDI device, and I have one, but you know, it was really cool technology, but I think it's now unnecessary. But what you could play like keyboards and that kind of thing. I really like the stringed accompaniment, that you could make string swells in the background. You could mix the guitar sound with these string sounds, and it sounded like you were having this accompanied performance. I used to use it a lot, and not with this guitar. Actually, I had several other guitars that have that pickup on it. And it's sort of a waste of money now, because I'll show in another video at some point. I'll demonstrate these electroharmonics. Let's think this up. I don't say the word much. Electroharmonics pedals that don't require that pickup, and they can make synthesizer sounds. Whoop, that's not right. How the hell did you? Gonna go blot the G. Nylon strings do not like to stay in tune. They're very sensitive. So this was not really good performance. Let's see the guitar here. See my hands. Here you go. This is a Love Song by Tesla. Whoops, I forgot it. Should we stop and record the whole thing over? I can't believe I'm like totally. Well, that sucks. Can't remember that either. That's what alcohol will do to you, kids. I was looking at it. See, I didn't think about it that time, and I did it. See, I used to be able to. I used to pick with these. When your correct style is to, for these three, to use your thumb, and then maybe even anchor with your pinky. I always rested my palm. I usually just use my thumb and my finger here, and then sometimes I'll use the middle. It's out of tune already. So that's really exciting stuff. Stay cool, kiddies.